Monte Carlo Localization, an AI project by Nels Frazier. First, let's be clear. We aren't playing games of chance here. Instead, we will apply the Monte Carlo method as a particle filter. To do this, we need a few pieces to puzzle together. Let's start with the motion model. Each particle needs to be able to move based on the robot's movement. So when a robot moves, the same motions are applied to particles. We can see this model in action here. The model has to handle rotation and translation for a robot moving on a planar surface. Next, we need a sensor model. Particles need to be able to sense the environment, similar to the robot. We can use ray casting techniques to sense obstacles in the environment, as seen here. This does, however, require a representation or a map of the world. Once a particle senses the world, it can compare its readings with the robot's real sensor readings. The difference in these readings weights each particle with its likelihood to be where the robot is. With these models in place, we can now simulate multiple particles in the Monte Carlo fashion. After all the particles update their positions and compare their sensor readings to the robot's, the particles are then resampled based on the weights derived from the sensor comparisons. So particles with higher weights are more likely to represent the robot location. Particles with small weights are moved to the location of particles with higher weights. Here, with 10 particles, we see a quick convergence to the location nearest the robot. Putting all of this together and adding enough particles to get a good distribution across the world, we can see the convergence of particles around the robot's position with a minimal amount of exploration. This technique can be used to determine a robot's location in a given world. With a few extra modifications, it can make it quite robust. One such technique is to redistribute the particles if their weights all become zero. This allows the robot to continue to localize even if it is moved to a new location without its knowledge. We can see this localization working at any starting location in the world. And even when the robot only senses in the cardinal directions, it can begin to converge on its true location fairly quickly. Another optimization is to create a new particle at random in the world if the particle makes a move that the robot could not. For instance, if the particle finds itself in a wall, this gives the particle a chance to end up in a much more likely place in the world. And finally, a powerful optimization to Monte Carlo localization is the ability to use different models for the motion and sensor models. More robust models can be used to deal with noise and various types of sensors and motors found in the real world. This can yield much more accurate results in real robots. So for this project, I implemented a motion model and a sensor model based on the simulated Scribbler robot. And we have seen how each of these works individually and how they are combined into a Monte Carlo simulation to probabilistically determine where in a given world a robot is. I hope you enjoyed, and thanks for watching.